So the first example that we're going to look at is the one that was here on the bottom about an object being pulled with an angled force. That means a force that is at an angle with respect to the direction of motion. So generally we're just told about the example in words, and it's our job to pass it to images and then to a free body diagram. So the example says that there's a pulling force that is angled, that is 28 newtons of force at a 20-degree angle from horizontal, and it's going to be pulling an object of a mass of 2 kilograms through a surface with the coefficient of friction mu k equals 0.15. So what we do there first is draw the situation. So we have the horizontal floor, we have our little object, and we're going to have a pulling force at 20 degrees. So it's maybe like this, could be 20 degrees. And this is our F pull. And we draw the 20-degree angle just so that we know what we're talking about. So our pulling force is 28 newtons at 20 degrees from horizontal. The mass, we can add it maybe here, just to remember that the mass is 2 kilograms. And the next thing that we know is that the friction here, the coefficient of friction, mu, is 0.15. So as we saw before, the next step is to draw the free body diagram. So we need to determine all of the forces acting on the block. As always, we always start with the force that always acts on every single object, no matter where they are or what they are doing, which is gravity. So we have a force of gravity that always points downwards, that we call Fg, and it's always given by the mass times 9.8, m times g. So in this case, we have m is 2 and g is always 9.8. So our gravity force is 2 times 9.8, which is 19.6 newtons. So that's gravity. Now, objects that are on top of a surface will always have a normal force acting on them. So we need to include normal force, which is always perpendicular to the surface. In this case, the surface is horizontal, so the normal force has to be vertical, which means it's exactly upwards, pointing upwards. So that's going to be our normal force. We don't necessarily know the normal force yet, because before, normal force had been equal to the weight, to the force of gravity. But now part of the pulling force has a vertical component, and that's going to affect the normal force. So we don't give it a value yet. We just write it as Fn. And finally, because we're told that there's a coefficient of friction, there must be a force of friction. So if the object is going to move in that direction because of the pulling force, friction tries to stop it, so it goes in the opposite direction. So friction is going to be in the opposite direction, to the left. And we have the equation for friction, which is always mu times normal force. I don't know if you guys can see that. So those are the 4 forces that are acting on the object. That is the complete free body diagram. The following step is, because there is one force that is in diagonal with respect to the motion, only one of them, because if you see this one is not in diagonal, this one is not in diagonal, and this one is not in diagonal, the only force in diagonal is the pulling force. So that's the one that we're going to have to divide into horizontal and vertical components. So that's what we do now. We divide it into, here we have an F pull horizontal. So maybe we can call it F pull H. And then we have a vertical component that we're going to call F pull V. So those are now our 2 components. And we need to remember the equations for the components, which are, when we have a force F at an angle theta, F cos theta is the horizontal component, and F sine theta is the vertical component, right? So in order to calculate these two, we need to do 28, which is the f, times the horizontal one would be cosine of the angle 20, and the vertical would be 28 times the sine of the angle 20. Once we have those two forces, we can ignore the pulling force because we already divided into components and we can forget about it and just use the other two. So these two numbers I'm going to put in my calculator. Give me 1 second. So we have 28 cosine 20, which gives us 26.3. And we have 28 sine 20, which gives us 9.58. And these are both forces, so they are also in newtons, just as the original force was. Okay, so that's the following step. What we need to do now, according to our rules, is to divide this problem into two separate problems, which is the horizontal component and the vertical component separately. So we always start with the component that doesn't have movement, because it just makes it a lot easier. So I have solved many of these problems, and I know that it's just a lot easier if we choose the one that doesn't have motion first. So the one that doesn't have motion in this case is vertical. So we ignore everything that is horizontal and focus first on vertical. So the first thing we do is identify all of the vertical forces. So each arrow here represents a force. So we count the number of vertical forces. So we have this one, the force of gravity, we have this one, the normal force, and we have this one too, the vertical component of the pulling force. So those three are the ones that are going to count on our vertical thing. The other forces are two horizontal and a diagonal one, which we can ignore. So for vertical and horizontal both, we're going to have to use Newton's second law, which is the sum of forces, or the net force, is equal to mass times acceleration. So the net force, if you can remember, is the sum of all forces taking into account their direction. So everything that goes upwards we're going to say is positive, and what goes downwards we're going to say is negative. So we have positive, the normal force, which we're just going to call Fn until we figure out what it is. And we're going to add the other positive force, which is 9.58. We know that one already. And now we need to subtract all of the forces that point downwards, which in this case is just the weight, or the force of gravity, which is 19.6. So we subtract 19.6, and we equal that to our mass and times our acceleration. So the mass, the problem gave it to us, it was 2. And the acceleration, if you remember, we had one component that had acceleration 0 and another had an acceleration unknown. In this case, we're talking about vertical, and since the object isn't going to move in a vertical direction, neither up nor down, the acceleration is actually 0. So we're going to get a 0 on this side. So if you notice, the only thing we're missing is the normal force. So we can actually solve for the normal force and find it right now. So normal force, everything that is added, we pass to the other side to subtract. 2 times 0 is 0, so we have our 0, and then we subtract 9.58, and we add 19.6. We put that into our calculator, so we get normal force is 0 minus 9.58 plus 19.6, which gives us 10.02. So our normal force, we found it already, is 10.02. That's one of our results, and it's the only thing we can do with vertical. We already used Newton's second law for vertical, and that's what we got, and that's all we can do. So we can move on to horizontal now. So we leave this there, separate this completely, and move on to horizontal. So in horizontal, we need to use the exact same equation. The net force is equal to mass times acceleration. But now we're not talking about vertical net force or vertical acceleration, we're talking about horizontal net force and horizontal acceleration. So The net force, again, is the sum. We're going to choose the right direction as positive and the left direction as negative. So the only horizontal forces that we have are the horizontal pulling force in positive, which is 26.3. So we put that there, 26.3. And then we need to subtract the force from the left, which is the friction force. The friction force, we have our equation, is mu times normal force. The mu, we got it from the problem, it was 0.15. And then we multiply the normal force. The normal force, if you remember, we just got it up here. It was 10.02. So we can use it now, 10.02. Those are our two forces. This whole thing is friction, and this was the horizontal component of the pulling force. Notice that we are ignoring the diagonal force because those 28 newtons were already divided into part horizontal and part vertical. So we don't use it anymore. We can ignore it. So we had our two forces, and this is going to equal the mass times the acceleration. Again, the mass, we have it. It's 2 kilograms. And the acceleration, we don't know it. It's just a. So we leave it as a because we don't know it yet. So we can solve this left part of the equation, because it's already all numbers. So we put that in our calculators. 26.3 minus 0.15 times 10.02, and it gives us 24.8. 24.8 is equal to 2a. So in order to solve for the acceleration, the only thing we're missing is to divide by 2. This 2 is multiplying the a, so we pass it to divide on the other side. So we get 24.8 over 2 for the acceleration. We put it in our calculator and it gives us 12.4. 12.4, remember the units, let me put this farther away. The units are meters per second squared. So that is our final answer. The acceleration of the block will be 12.4 meters per second squared in the right direction. So that's it. That's how you solve this problem for the horizontal acceleration of the block with an angled force.